Okay, so welcome back to particle physics and the standard model. This is lecture 23. So in the last class we started looking at spin 1 field configurations and we understood that for a massive spin 1 particle you have 3 degrees of freedom. In addition to the transverse degrees of transverse polarizations, you also had a longitudinal polarization, correct, and the longitudinal polarization is exactly what we should infer as the presence of a non-zero mass, right. And then we wanted to embed these 3 degrees of freedom into a theory using a 4 vector, which is the next non-trivial representation of the Lorentz group, right, as opposed to a scalar. So we started with the one Lorentz invariant equation of motion that we know, which is the Klein-Gordon equation, constructed a suitable Lagrangian and found that even this is not a successful program. Why? Because first of all, this does not actually describe a 4 vector. This describes 4 independent scalar propagating modes made to look like a 4 vector, because the Klein-Gordon equation here acts independently on each of the components, right. So it is actually 4 scalars sitting as a vector, showing themselves as a vector, right. But more troubling is the fact that if you compute the energy density from the energy momentum tensor, you find that there are some of these independent modes that carry negative energy, so they are not positive definite, right. So what should we do? We should try to look for other Lorentz invariant terms that can be written down in Lagrangian and see what the equation of motion gives us, okay. So until now we have been doing the reverse, we guessed the equation of motion and then we got to the Lagrangian, but we should start getting used to the art of guessing what the terms in a Lagrangian should be and then normalizing it suitably and so on, okay, because the Lagrangian which gets into the action is more fundamental than the equation of motion itself, right. The Lagrangian is what actually knows about the symmetries in your problem, alright. Let us see, do we have another Lorentz invariant term here? It turns out that indeed we do. There is one more Lorentz invariant kinetic term, because remember there is a kinetic term, right. Can you guess what that could be? You just have to manipulate the contravariant and covariant indices to see what that should be. That is simply let me slightly rewrite it, that is simply contraction of covariant and contravariant indices between the field and the derivative. That is absolutely possible, right. Why should I only contract derivative with derivative and field with field? I can also do field with derivative and derivative with field. I just need Lorentz invariance. Agreed? Okay. Now with this term, let us see if we can write down a generic Lagrangian. So I am going to call the coefficients A and B, okay, because it is a generic Lagrangian. So I start with this Lagrangian that we had already, okay. Notice that I have moved some of the fields around, I am moving I have rearranged the order of the field and the derivative, correct. That is totally possible because I can do integration by parts and then I will end up with a total derivative term which vanishes on the surface in the action, correct. We have been doing this all the time, correct, even in classical mechanics. So that is what I am doing here. So I write A mu dou mu, okay. This is the new term that we introduced, and of course not to forget the mass term. This is a perfectly Lorentz invariant Lagrangian. Okay, okay, very good. Now with this, notice already that this B term, right, forces A mu to be a 4 vector already. I did not have that luxury here, I did not have that over here, correct, because the A mu and the A mu terms contracted with each other. So they could have split into 4 different A square terms, right, A0 square plus A1 square plus blah blah blah, A0 square minus A1 square minus A2 square plus minus A3 square, right. But now I do not have that, because explicitly I am forcing the derivative, these two to contract, the derivative to contract with the A mu and this to contract with the A mu. So explicitly I am writing down A mu as a 4 vector. Okay. So you can already see this is an even better candidate than before, correct. Now let us do other tests. Let us check what the equation of motion is. Okay. So what is the equation of motion? I get the A term gives me this, the B term still contracts derivative with field, and the mass term just goes for a ride. Okay. Now keep this in mind, we are going to come back to this equation of motion. Okay. This still has not told me that I have embedded 3 degrees of freedom into a 4 vector, right. To see where that has happened, I am going to take the derivative of the equation of motion itself, okay, this being the equation of motion out here. What happens if I do that? And I am taking a derivative with respect to the mu index, okay. Then I get, do you agree that A and B now get together and I am left with the box term, agree, the mu here now hits this mu, right, and I can do a change of indices, basically I end up with a box term, correct. Okay. What else happens? So I can also pull out the mass square term, and at the end of the day the partial mu term just eats the covariant index of the A term. Can you see what I have done? I have basically changed, over here I have just interchanged mu and nu, because these are just dummy indices, right. And then I pulled out an A mu and made sure that the box term comes out. Okay. So this I am going to set to 0. Okay. Now either this term is 0 or this term is 0, correct. Which one should I actually set to 0, or should I set both to 0? Now here is the thing, okay, generically this term is not 0, correct. Even if I set A equals minus B such that the box, there is no kinetic term over here, right, as long as I have m square not equal to 0, right, because I have the freedom to choose A and B, but I do not have the freedom to choose m squared generically. As long as m squared is not equal to 0, I am only left with one option, right, which is this derivative is what goes to 0. Okay. Now I am going to tell you that this is what removes one extra degree of freedom that we had in the problem, right. A 4 vector is made of 4 components, right, and our job was to remove one of them so that we could embed exactly the 3 propagating degrees of freedom into the equation of motion, correct. And if I have a condition like this, it means that I can always choose A1, A2, A3, A4 such that as long as I satisfy this condition, I have removed 1 degree of freedom. And there are only 3 now left in the propagating field, correct. Okay, that is not all though, alright, because not only have I removed this extra degree of freedom by doing this magic, right, I have also done it in a way that makes this constraint itself Lorentz invariant, and that is important. This is a Lorentz invariant constraint. Okay. So why is that important? Because I have removed exactly the representation of the Lorentz group that I did not want to begin with. Okay. So what do I mean by that? Remember that the Lorentz group, right, which gives you transformations, right, on 4 vectors. The Lorentz group is an SO13. Why 1, 1 is for the time component and 3 is for the spatial components, right. So you do all these Minkowski transformations, correct, transformations on Minkowski space, correct. So this intuitively for 4 vectors you can see there are 4 degrees of freedom over here, right. So in some intuitive notation I am going to write down that because you have 4 vectors there is a 4 representation, correct, for the Lorentz group which can break down into a 3 and a 1, agreed, where the 3 corresponds to spin 1 fields, right, which we just saw you need to have 3 degrees of freedom, and 1 corresponds to spin 0 fields, right. So what does this notation mean? Remember we talked about representations, right, and then we talked about reducible and irreducible representations, right, of a group. What we are looking at is a representation of a Lorentz group where you represent all the transformations with 4 by 4 matrices and then you use 4 vectors, right. So that means you can call that representation of 4, and because you have 1 time component and 3 space components, you can break it down, you can basically reduce that group to a 3 and a 1, it turns out. Okay, this is one of the ways you can reduce the group. There are many ways to reduce the group. This is actually one of the ways in which you can reduce the 4 of the SO13 group. Okay, and of course if you do that then the 3 has to correspond to a spin 1 which we just saw, and the 1 has to correspond to a spin 0. Yet another way to see this is that remember in Maxwell's equations, right, the A mu when we introduce this, right, how do we do this? This was basically a 4 vector potential, correct. So you had a scalar potential and a 3 vector potential, correct. So already you see that they are kind of 2 different beasts, right. They get into the definitions of the electric and the magnetic fields differently, right. So that already gave you a hint that there is a scalar sitting inside this A mu and a vector sitting inside the A mu, and this is what we are aiming for, correct, for 3 degrees of freedom, right. It is not quite a 3 vector in real space, a spin 1 particle is not that, but this gives you an idea of how this breaks down. into a 1 under 3, right. And what we have done now is, since this is a Lorentz invariant constraint, we have removed an entire representation of the Lorentz group. And of course, what representation would it be other than this, right? There is only one constraint, there is one degree of freedom we have taken. Since it is Lorentz invariant, this entire representation has been removed, and we are left with a 3, which is just what we want. Even under the Lorentz transformations, this is just how we want the 4 vector to behave. Okay, so I will just write that down explicitly. Removed unwanted spin 0 component. Remember that in our earlier treatment, this was kind of the problem we had, right. We ended up with, although we wrote this down as a 4 vector, it was actually secretly 4 different scalars, right. In other words, earlier what we had was that, so let me say, earlier the 4 was actually a 1 plus 1 plus 1 plus 1, okay, and so each of them were independent propagating modes, and that is why we ran into the problem before, and we could not remove any of these using any constraint, right. But if we now transform the whole thing as an actual 4 vector, this is always possible, okay, good. So that is what we have done. Now, having done that, let us move on to rewriting the Lagrangian with this condition, okay. So I am going to rewrite the Lagrangian as half a mu, there is still a box, and then I am going to actually enforce a equal to minus b, because I can always do that, and then it turns out that is when I get the correct normalization for the Lagrangian, correct sign for the energy density, and I also get some very nice features like gauge invariance, which we are going to see soon, okay. So I am just going to make use of that freedom, okay, that is what I have done here, okay. Now notice that I can now rewrite this further. There is going to be some redundancy, but bear with me, because this leads to a very interesting looking Lagrangian. I am just going to add and subtract some terms, so that I can condense the whole thing, okay. Give me a second. So this is what we have now. You can see what I have added and subtracted, right. You can see the terms that I have introduced, okay. Now what I am going to do is define this whole object as an f mu nu. Do you agree that this is a tensor now? A Lorentz tensor of rank 2, right? There are 2 indices, right? And of course I hit it with another with upper indices, and the mass term goes along for a ride. Remember this f mu nu? Of course you do, right? This is nothing but the Maxwell tensor. Remember we wrote this in terms of E's and B's, correct, in the covariant formulation of Maxwell's equations. That is exactly what this is, okay. Now in field theory we call it by a different name. It is the field strength tensor. And since it is a tensor, again I need to have covariant and contravariant indices, as I do, and this whole term is of course a Lorentz, this whole thing is a Lorentz invariant structure. All the indices are correctly contracted, correct? Okay. So that Lagrangian has a name, let me just write it here. This is called the Proca Lagrangian. For a massive spin 1 field, the Lagrangian that gives you the correct degrees of freedom is called the Proca Lagrangian. Okay. And that gives rise to the equation of motion also, which is called the Proca equation. Okay. And that equation of motion looks like this. So d mu nu f mu nu plus m square a nu equal to 0. Okay, that is your equation of motion. Good. Remember, if I did not have m square, what is this? This is one of the two Maxwell equations, right, in covariant form. Agreed? Of course, for source free terms, that is what we are doing here. Now with a mass added, this is what you get. So one fun exercise that you can do is to now use this equation of motion and go back and write the Maxwell's equations for a massive field, okay, and see how things look like. Alright. You do not have to introduce a source term for this. Okay. Now this form of writing it, to me at least, it looks a bit confusing. So I prefer the expanded version of this. Okay. So what I like to do is to expand this and write it as two different equations, one for the a mu part, well, both are for the a mu part, but with two different meanings. Together, I mean, this is exactly equivalent to that. Okay, you can convince yourself, go expand this and see. I like writing it like this because it helps me see what each of these equations actually mean. This is like a, like a Klein-Gordon equation now. So Klein-Gordon-ish, I am going to say. That tells me that there are propagating degrees of freedom, but that is meaningless without the other equation, which is the gauge fixing. Sorry, let's that is not gauge fixing, which is a removal of the scalar degree of freedom. Scalar degree of freedom removed. Okay, very good. Now this condition has a name, the condition that we put in by taking the derivative of the equation of motion, right? What is the name? It is a slightly confusing name. It is called a Lorentz gauge condition. Notice that I said Lorentz, I did not say Lorentz, right? Let me write that down. So it is not equal to Lorentz. This really used to confuse me. That is why I am saying this, it confuses everybody. Many people still say Lorentz because it does remove a Lorentz invariant term, but Lorentz is a completely different guy. Okay, so this is the guy who found the gauge condition that you need. Well, it is not really a gauge condition, it is a condition that comes from the equation of motion, but removing the degree of freedom this way was due to Lorentz, completely different guy. Alright. Okay. Now one neat thing can already be seen in the Lagrangian when you write it this way. Okay. Remember way back when we were looking at some Feynman, when we were in the lecture on Feynman diagrams, I said that certain interaction terms are allowed and certain other interaction terms are not allowed, right? Certain interaction vertices are allowed and others were not. And one of the things I said was that an interaction vertex like this for photons, I said, was forbidden, right? And I didn't tell you where that came from. Now you see where that comes from. This means I need 4 photons in a vertex, correct? Do I have 4 photons anywhere here? Absolutely not. I have at most 2 photons, correct? So this all comes from the Lagrangian, okay? Similarly, I don't have a 3 photon vertex either, right? I can only start with a 2 photon vertex for a dimension 4 theory. This is all, the lowest order terms that you can write down basically. Agreed? Okay, very good. Now let me just add one more thing. When we get to gluons, right, I had said that for gluons this was allowed and the 3 gluon vertex was also allowed, right? We will see that for gluons we don't write the field strength tensor this way, okay? The field strength tensor here was just dou mu a nu minus dou nu a mu, right? There will be extra terms in the field strength tensor. That is the way you can make what are known as gauge invariant terms, which we will see in a second, okay? So that is the way you can write down a fully symmetric Lagrangian for theories like quantum chromodynamics, and from those you will see that you cannot help having 3 gluon and 4 gluon vertices, okay? So we will catch up with all this soon. Very good. Now there is one other thing we need to check, okay? All of this has been a success so far, but we are still to check the positive definiteness of the energy density, right? Okay. So the energy density, I encourage you to now go use the energy momentum tensor, get the T00 component, go ahead and find that you are getting something sensible. You get an E square plus B square over half over 2 plus a mass term, and thankfully everything that it multiplies is positive definite, okay? So that is effectively what you get at the end of the day, and that is of course positive definite, right? So this term you are familiar with, that is of course the energy density coming from the E and the B fields, right, from electromagnetism, kindergarten electromagnetism, right? This is the new term here with the masses, but thankfully the fields also, both the time component and the spatial component, come as squares. So good. So all the requirements that we need are satisfied and we can declare victory, okay? So the Proca Lagrangian is indeed the theory for embedding a spin 1 massive particle into a 4 vector, okay? Now in the last few minutes of the lecture I am going to wrap up with something very curious that has already happened as we wrote down this theory, okay? There is a reason why I contracted these the combination of derivatives and fields into the F mu nu notation, okay? Not only because it is so cute and then you can just write it down and then you can make connection with the field strength, the Maxwell tensor, but also because this explicitly carries another symmetry which will turn out to be very important for us as we construct the standard model, okay? And that is You are getting a taste here already of what is known as gauge invariance. Okay? What do I mean by gauge invariance? F nu nu, right? Even though it is a Lorentz tensor, it is still invariant under the following transformation. If I take A mu nu to some A mu nu plus, this is an alpha here, derivative of some alpha of x, okay, for any function alpha of x, okay. Under this transformation, notice that F nu nu is indeed invariant. Do you agree? I have a dou mu over here. I have I'll have the cross terms will basically be dou nu dou mu alpha of x minus dou mu partial nu of alpha of x. That's just 0, right? Those are the cross terms that I need to account for. The rest is still the a mu a nu terms, right? So, isn't this interesting that under this non-trivial transformation where I have a derivative here, this entire tensor is invariant. Said differently, right, I can change how I describe my field. There is a redundancy in the field description. If I had used this as the field in the Lagrangian and not just a mu nu, I could still have embedded all the 3 degrees of freedom into this 4 vector. This is what I would now call a 4 vector, right. So, gauge invariance is basically a redundancy in description of fields. This is, if you forget everything else in this course, you should never forget this. This seems to be the supreme, the most supremely important symmetry principle that we use to construct Lagrangians to describe the real world. Okay? This redundancy has to be built in. It turns out that wherever you find a theory with this redundancy, that seems to describe the real world best. Okay? So, we will take this up in more glory later. I'll just leave you with one final comment. Notice that the field strength tensor is invariant under this gauge transformation, but the Proca Lagrangian itself is not. The Proca Lagrangian is not gauge invariant. Why? Because of the mass term, right? Because of m square not equal to 0, right? So, this term is still not gauge invariant. This is, hence the combination is. Okay, good. So, I will leave you there, and then in the next class we will take up spin 1 for a massless field, okay, and we will see interesting things that come out of this. Alright, thank you. See you in the next class.